It's like this call.
Here's the next one. It's going to be here's the x-axis, here's the y-axis. We're going to have a plus charge here. Okay, let's call it, so Q1 is going to be positive Q, okay? Q2 equal to minus Q, okay? Minus Q. And let's say the distance from here to here is called D over 2 or A over 2? A over 2. So it's A over 2. And from here to here is A over 2. Okay? Both are A over 2. Okay? And then we would like to find the electric field here at the distance, let's say, D. This distance. Distance from here to here is D. So what's the electric field at this point here? And let's give it a color. So it becomes the red one. What's the electric field? Total electric field at the red point. So first, in what direction do you expect? In what direction is the electric field due to the plus? Like this? Yeah. How about the minus?
Attracts.
Towards it, right? So towards means this way. So the total electric field would be in what direction? Yeah. So this one is down to the right. This one is down to the left. So left, right, and left cancel. So we expect the total electric field to just be this way. Will be in the minus j hat direction. Total electric field will be in the minus j hat direction. So we're going to find it. So the total electric field would be the electric field due to the plus charge plus what? The electric field due to the minus charge. All right. So it's going to be the electric field due to the plus charge. I'm going to call that E plus, electric field due to the plus the electric field due to the charge that's minus. All right. Okay. Electric field due to the plus charge is K times the charge. How much is the charge? Just Q, right? Okay. Should we use the form that involves cubed or just or the one that involves square? Cubed because the r hat is not easy to determine. Good. So cubed. So what's this distance? Let me right here, from here to here. Let's call that r plus. It's going to be or with a vector, right? It's going to be what? D I hat minus A over 2 times J hat. Good. So let me here R plus the magnitude is going to be D squared plus A over 2 square root, right? And so R plus cube is going to be D squared plus A over 2 squared to what power? Yes, we did this earlier. 3 times. So that's going to go here. D squared plus A over 2 squared with 3 halves. Okay. And then times the vector R plus. What's the vector R plus? Good. Okay. So this takes care of what? This part. There's the A plus. Good. We're going to do the E minus now. The E minus is going to be very similar. Not the same though. Very similar. K times the charge, what's E2? It's minus Q over the distance from the minus charge to the red point. It's the same, so this is going to be the same. This part is going to be the same. So D squared plus A over 2 squared over 3 halves. And now the vector itself is going to be what? Good. D I hat plus A over 2 J hat. Yeah. Got it. Yeah. The J hat, yeah, there is an extra minus sign that makes this minus and this minus. So actually only the J hats survive. The I hats are the ones that, so as we predicted, we said it's going to be, it will end up being pointing downward. Yeah. So yeah, the J hats will cancel because there is this charge is minus. And the height, so the I hat will cancel, the J hat will double, right? But it will be negative. So I'm going to just do that. So if you double the J hat part, the A over 2 and the A over 2, when you add them, you just get A, right? You get double, and you will end up with a minus sign. So let's take care of that. So you have a minus sign. You have K, Q, and then A. And then D squared plus A over 2 squared to the 3 halves J hat. Okay. That's the electric field. This thing here is called a dipole. It's a dipole because there is a positive pole and a minus pole, negative pole. One is plus, the other one is minus. 2 poles. Okay. So this brings me to the discussion of dipoles. I'm going to discuss dipoles, define what a dipole is, and then we will do some things with dipoles. Is that a hand? Or?
Yeah. So we don't have I hat because it canceled out?
Yeah.
Okay.
Yeah, the I hat canceled. You see, this one, the I hat is positive, right? There is a minus here, so eventually this will be minus, this will be minus. So this I hat will be minus. So dipoles, ready to introduce them? Yeah. Or to meet them? So let's talk about that. Yeah, so next time I'm going to do this. We'll talk about dipoles today, and then we'll find the field due to the dipole on the axis and halfway. And then we will do the torque on the dipole. In the notes, the torque is delayed till the end, so I will do that. So let's get the dipoles out of the way, and then we'll just focus on calculating electric fields due to continuous charge distribution. So that's what I'm going to do. So dipoles. So the dipole moment dipole moment is given the symbol P. So this quantity P called the dipole moment. So P is not pressure, it's not momentum, it's the dipole moment. Okay? And you can tell from the context. So P here is used, it's the symbol P but used for different context. It's not the power either, it's just dipole moment, P. So how do we define? It's defined this way. P is equal to, and I will not write anything yet. I need to draw something. Here's the x-axis. Here's the y-axis. Let's say I have a positive Q here at position R1. So this is Q1, which is positive Q. Okay? And then I would have another charge called Q2, but it's going to be positive or negative? Negative, it's a dipole, so we expect different charge, so a minus charge, here is a negative. So this is Q2, and it's just minus Q. So it's exactly the same magnitude, but minus. One is plus, one is minus. And this is R2. Okay, R2. So R1 is at position, Q1 is at position R1, and Q2 is at position R2. So what's the definition of the dipole? So here's the definition. So it's just simply, this is how it's defined. It's defined this way. It's Q1 times R1 plus Q2 times R2. Okay. So that's the definition of the dipole. So let's apply this definition to what I have in the figure. What's Q1 in the figure there? Just plus Q1, Q. So QR1, and then Q2 is, it's minus Q, so minus Q, and then R2, right? That's factor in Q. So we get R1 minus R2. Who can tell me this vector R1 minus R2 would be in what direction?
In between R1 and R2.
Between R1 and R2. Does it point from the minus to the plus or the plus to the minus?
The negative x direction, plus the y direction.
It's from the minus to the plus? Yeah. Yeah, it points this way. I tell you what, you will see in a second why that's the case. You can double check. R1 minus R2. This is R1 minus R2. It's a vector that points that way. Let's double check. Let's do this. What happens if I add this vector, R2, plus this red vector? What do I get? This vector plus this vector. What do I get? R1. I get R1. So these two vectors, they get me here. Look at what R1 does. It gets me there. So yeah, so I can double check that. So R1 minus R2 is a vector that points that way. Right? Now this vector, R1 minus R2, is given a name. The vector that points from the minus to the plus is given a name. It's given the name S. Like this. S. So we can S. S is just equal to R1 minus R2. So S always points from R1 to R2. From the minus to the plus. From the minus to the plus. So I'm going to put a couple of notes. Notice. I want you to notice a couple of things about S. S is equal to R1 minus R2. Okay? It points from where to where?
Negative.
From the minus to the plus. Its magnitude is what? How big is S? No, just from the picture. It's the distance from. Yeah, the distance between the two charges. It's the distance from the plus to the minus. Its magnitude is the distance from the two charges. The distance from the distance between the two charges, right? That sounds bad. Okay, it's the distance between the two charges. So, if you have a charge, a plus and a minus, let's say here is a minus, here is a minus, here is a plus, and let's say, then how would you draw the vector S in this case?
From minus to
From minus to plus. And if you're asked how much is the dipole, well, the dipole is just going to be the charge times the distance between them, which is just S. If you put a vector, then you get a vector. So that's the definition of this dipole moment, and so we'll see how we can use it. The idea of the dipole moment is this. I have 6 minutes, right? So here is a, suppose one is plus, one is minus. Let's say red is plus, blue is minus. They are near each other. Let's say they're at the same position. They're right on top of each other. What's the total charge I have? 0, right? The net charge I have is 0. 1 plus, 1 is minus. They're exactly the same magnitude. What's the electric field due to both charges? What's the net electric field due to these two charges here?
0.
It's 0. Both of them, they produce exactly the same electric field, but one is this way, the other one is away, right? One is plus, one is minus. So you should get 0 field if they are right on top of each other. But what if they're not right on top of each other? They're separated a little bit. Here is a small distance between them. And I'm here. Red is plus, blue is minus. Which field is going to win, the plus or the minus? The plus. So there will be a net field this way, the positive field. There will be, even though the net charge is 0, there will still be a net field because they're separated. They're slightly away from each other, right? So the question is, what's the electric field if this is called the axis of the dipole. If I'm just along this, what's the electric field away from them, a distance r, along the axis of the dipole? And then the second question, we're going to do it for 2 special cases. What's the electric field halfway, like on a plane that bisects this way? Surprisingly, no. Yeah, we'll do it. It would not be quite 0. So that's what we're going to do next. Good guess though. So that's what we're going to do next. So it's one of those where I have not enough time to start anything, but enough time to say something.